Agarwal, Assistant Professor, JSS Academy of Technical Education, Noida. Today in this lecture, we are going to cover the topic paging and virtual memory management. Now, paging is basically a memory management scheme that allows the physical memory address space of a process to be non-contiguous. In contiguous memory allocation, what we have to allocate continuous locations to a particular process, but at all times it is not possible that we have contiguous space available for a process. So, in that case there comes in picture non-contiguous memory allocation. Now, in non-contiguous memory allocation we implement it using paging. Paging it is basically used for non-contiguous memory allocation, where it avoids the problem of external fragmentation and also avoids the need for compaction. Now, what we do basically here, the physical address space of a process can be non-contiguous. The process is allocated physical memory whenever the later is available, right. So, when we have the later is available, that time we allocate that memory to the particular process. So, what we do here, we have two address spaces. We have logical address space that is generated by the CPU, and another one is the physical address space where the process is actually stored, right. So, what we do, we divide our logical address space and physical address space into equal sized blocks, right. Now, the blocks in the logical address space are termed as pages. In logical address space it is pages, and in physical address space it is called a frame, right. Now, what we need? We need, one of the requirements is that the size of the page and the frame should be equal. Why? So that one page can fit into one frame of the physical memory, right. So, this is what we have here. We divide the physical memory into fixed size blocks called frames, that is normally taken to be the power of 2, and it ranges between 512 bytes and 8192 bytes. This is a standard norm that we take. Now, the logical memory is divided into pages. Now, when we divide the logical address into pages and physical address into frames, and what we need, we have to fit one page into one frame. So, what we need to keep track of all the free frames that are available, because only when we have all the free frames available, then we can place one page into one frame. So, to run a program of size n pages, we need to find n free frames and load the program. Okay. So, basically now what we do? We have our logical address space that is divided into pages and physical address space that is divided into frames. Now, we need to convert our logical address into physical address. Now, this is the address generated by the CPU. Now, you can see here we have two parts P and D in the logical address. Now, logical address is basically divided into two parts. One is the page number and another is the page offset. Okay. So, page number is what? It is basically used as an index into a page table which contains the base address of each page in physical memory. Let us say we have one page, page number 2, that this is stored in physical memory in one particular frame, and that frame will be starting at a particular location in the physical memory, right. So, this page number P is used as an index into the page table, where we will get that in physical memory where this page is actually located. That means, the starting location of each page is given through the page table. The second part is page offset. Now, page offset, it is represented by a letter D. Now, D is what? It is basically the displacement within a page. Okay. For example, we have one page of 1 kilobytes. Then in 1 kilobytes, at which location, which address we are exactly looking for, right. Suppose we have 1024 locations in one page. So, within those 1024 locations, which page we are which address we are going to access, this is given by the page offset, right. So, now we have got to know that the logical address is divided into two parts, P and D. Okay. Now, let us say we have a logical address space of 2 raised to power m and the page size is 2 raised to power n. Okay. So, the total number of bits required are m for logical address, because it is 2 raised to power m. If we have 2 raised to power m size, then the number of bits required is m. So, logical address is of total m bits. Okay. Now, the page size is 2 raised to power n. Okay. So, here what we have, we are dividing the logical address into two parts, P and D, where P is the page number, that is represented by m minus n number of bits, okay, and D is the page offset, which is represented by n. Now, why D is represented by n? Because D is what? Page offset, that means displacement within a page, okay, and the page size is 2 raised to power n. So, how many bits do we need to represent an address within a page? We need n number of bits. Okay. So, n number of bits are here required for the page offset and the remaining bits are for the page number. So, this is how we divide our logical address into two parts. One is the page number and another is the page offset. Now, this is the paging hardware. It basically tells us how a logical address, that means the address generated by the CPU, is converted into the physical address, right. So, here what we have our CPU that generates the logical address. Now, the logical address, this is your logical address, that is divided into two parts, P and D, as discussed in the previous slide. Okay. Now, P is page number and D is page offset. Okay. P is your page number and D is page offset. So, now this P, the page number, goes to the page table. From here it goes to the page table. This page table is an index that tells us that a particular page is located in which frame of the physical memory, right, or you can say that at what is the starting location of that particular page in the physical memory. Okay. So, let us say we have one page here and we have got the location from here, that is your this is your F, that is your frame number. From here the frame number is fetched and it goes here. Okay. Now, we have got the starting location. Now, once we have reached the starting location, then after that where we have to go, that is given by the page offset, and this from here goes to here, where frame number collectively with page offset gives you the exact memory location where it is located. Okay. So, this is basically the paging hardware. Just taking a quick glance over it, the CPU is generating the logical address, which is divided into two parts, page number and page offset P and D, which then goes, the page number goes to the page table, from where the frame is fetched, the frame number is fetched, and the frame number combined with the offset gives us the exact memory location in the physical memory. Okay. Now, for example, here you can see this is our logical memory. Here we have 4 pages, page 0, page 1, page 2 and page 3, right. Now, this is our page table that gives us an index. What is this telling? Page 0 is located in frame number 1. You can see here page 0 is located in frame number 1. Page 1, it is located in frame number 4. Page 1, it is located in frame number 4. Page 2, it is located in frame number 3. So, this is page 2 located in frame number 3. Then page 3 located in frame number 7. Here page 3 located in frame number 7 of physical memory, right. So, this is how the logical address is mapped into the physical address, and a page is placed into a frame of the physical memory. Now, next comes the concept of virtual memory. Now, virtual memory is basically a term that lets the user use a much bigger space than the physical memory. Now, physical memory is limited in size, we cannot extend it to after a particular limit, right, but the processes are quite large in number and big in size. So, all of them cannot be accommodated in the memory at the same time. Okay. So, what we need to do, we have the concept of virtual memory, the memory that actually does not exist. The name itself tells virtual. Virtual means that does not exist actually. Okay. Basically, the backing store itself works as a virtual memory, but it is transparent to the process, to the user. Okay. The user feels as if a big memory is at its disposal. Okay. So, the concept of virtual memory allows a large number of processes to be in the main memory at the same time. Okay. And for this, what we do, the process, the module of a particular process that is required, we bring only that particular module into the physical memory. Okay. Rest all is in the virtual memory. Fine. So, it is basically a separation of user logical memory from physical memory. Only part of the program to be executed needs to be in the memory. If a part of a program that need not be currently executed, that we need not save into the physical memory at that particular point of time. Now, logical address space can therefore be much larger than the physical address space. It allows the address space to be shared by several processes. Now, in the diagram here you can see we have a virtual memory where we have n number of pages, page 0, page 1, page 2 up to page V, right. then we have a memory map, okay, where we know that how this page will be mapped into the physical memory. This is our physical memory where actually the process is stored, okay, for execution. Now, this is what? This is our backing store. This is our backing store where actually the processes are residing. So, now if a particular module, a particular process is required for execution, then it is brought from the virtual memory through the memory map into the physical memory. If it is not there, then the backing store is concerned, and then from here the process is brought into the physical memory. Now, depending upon the algorithms that we use, we decide whether that particular page will be there in the virtual memory or not. If it is required for further execution in near future, then we will keep it there, otherwise it will remain in the backing store. Now, virtual memory is a concept basically that can be implemented via two techniques, demand paging and demand segmentation. Now, demand paging and demand segmentation. Here in this lecture we are going to cover this particular topic, demand paging, but just to give a quick overview of what is demand segmentation also, let me cover this one first. Segmentation is basically a concept where we divide our address space into unequal number of blocks, unequal size of blocks, right. Like in paging what we do, all the pages are of same size, okay, and correspondingly we have frames that are of same size. But in segmentation what we do, the segments are not of the same size, they are of variable sizes depending upon the requirement. Suppose there is a data section that is very large in size, then we have a big segment. Suppose we have a segment that has only declaration part, that will be a small segment, right. So, segmentation is that term where we have blocks that are of variable size, okay. Now, the main term here is demand. What is this demand? Demand, as the name tells, that when it is needed, okay. So, in demand paging what we do, demand, that means when a page is demanded, or you can say when a page is needed, only then it is brought into the memory, otherwise it will not come and it will stay in the backing store, okay. So, only when a page is required, then we bring it into the memory as per the requirement. If we talk about demand segmentation, here the page will be replaced by the term segment, that is the only difference, okay. So, let us come back to demand paging. Here what we have, now when a page is needed, it is referred, first of all it is checked for a valid or invalid reference. What do we mean by valid and invalid reference? Valid means the page belongs to that particular process, that means the page is valid. If it is I, that means the page does not belong to that particular process and it is an invalid reference, okay. So, now if the reference is valid, then what we check, whether the page is in memory or not. If it is not in memory, then we bring the page into the memory. Now, we have a module that brings a process into the memory, and that is called as a swapper, right. So, swapper basically brings a page in and out of the backing store to the physical memory. Lazy swapper means that it brings the process only when it is required. If it is not asked for, it will not bring the process. Okay. So, here we are talking about pages rather than a process. So, rather than using the term swapper, we will use the term pager. Okay. That means pager is a module that swaps in or out the pages as per the requirement. If a page is required, it will be brought in, otherwise not, right. Now, this is the transfer of a paged memory to contiguous disk space. We have a program A that has 4 pages. These are swapped out and brought into the backing store. Okay. Now, these 3 pages are belonging to program B, and these 3 are being swapped into the main memory. This is what a swapper, or you can say a pager, does, right. It swaps the pages in and out of the memory. Now, when we talk about demand paging, that means we are referencing for a particular page when it is required. When it is required, only then we check whether it is there in the memory or not. So, if it is there in the memory, that means it exists, but if the page is not in the memory, that means there is a page fault. Okay. So, the first reference to every page is a page fault. Obviously, when the process is coming in, or the page is coming in for the first time, so that will lead to a page fault. Okay. So, by looking at some another table, first of all we check for that valid and invalid reference, because if it is an invalid reference, that means the page does not belong to that particular process, then we say we abort the process, because the page does not belong to that particular process. Now, if it is a valid reference, then we just check whether it is in memory or not. If it is not in memory, then what we do? The steps we follow are, we get an empty frame, so that we bring the page into the memory, we swap the page into the frame, then we reset the tables that we have, the page table and all, so that the updated data is there. Then we set the validation bit equal to V, okay. That V means, now here V means that the page is in memory. If it is I, that means the page is not in memory, okay. It does not mean the page does not belong to that particular process. Here in the page table, it means that the page is not in the memory, or the page is in the memory, okay. And then restart the instruction that caused the page fault. These are the steps that are followed. It will be more clear in the upcoming slide, where it is depicted with the help of a diagram. Now, here we see the steps in handling a page fault. First of all, we have an instruction load M. Here it refers a particular page. This is the first step, reference. It refers a particular page in the page table. If it is I means it is invalid. It does not mean the page is invalid. It means it is an invalid reference. That means the page is not in memory. Okay. So, it traps the operating system. The operating system gets to know that the page is a valid page, but it is not in memory. So, it has to be brought in. So, it goes to the backing store where the page is located. From the backing store, it brings in the missing page in the free frame of the physical memory. So, where we have a free frame, there we put that particular page. Okay. Now, after the page is located in this free frame, then this page table is reset. What we need to reset? We need to reset this I. Now, it will become V. This will become V. Right, that means a valid page, that means the page is in memory. Okay. And then after that it restarts the instruction and then the process follows. So, these are the steps: step 1 reference, step 2 trap the operating system, step 3 page is in the backing store, step 4 bring in the missing page, step 5 reset the page table, and step 6 finally restart the instruction, right. So, these are the steps in handling a page fault. Now, then comes the performance of demand paging. Now, till now we have done what is demand paging, how it is actually done, but now what about the performance? How do we decide that demand paging is giving us a good performance or a bad performance? So, this is decided by a term that is called as page fault rate. Page fault rate is what? Basically, it ranges between 0 and 1. Now, page fault rate means when a page is referenced, whether we got the page or we missed the page, right. So, when we refer a particular page, that time we get the page in the memory, that is a page hit, and if we refer a page and that is not in the memory, that is a page miss, right. So, the values that we talk about 0 and 1, if there is no page fault at all, that means every time we refer a page we get it into the memory, then the page fault is 0, right. That means there is no page fault. On the other side, if every reference is a page fault, that means every time we refer a particular page and that is not in the memory, that is a 100% page fault, and that will give you the value 1. So, 0 and 1 are the extreme values of the page fault rate. Then another term that we use for calculating the performance of demand paging is effective access time, EAT, EAT, right. Now, EAT is basically calculated by using the page fault rate and the memory access time along with the average page fault service time. The formula is very simple: 1 minus P into memory access time plus P into the average page fault service time. So, this is all average page fault service time, that means the time taken for a page to swap in, to swap out, to restart the instruction, all the overheads including, they make the average page fault service time, right. So, by just using this formula we can calculate our effective access time. Now, just quickly we will go through an example. Let us say we have our memory access time of 200 nanoseconds, right, and average page fault service time is 8 milliseconds. Then we can easily calculate effective access time, that will be 1 minus P into 200, 200 is the memory access time from here, plus P into 8 milliseconds, that is the plus P into average page fault service time. So, by calculating we are getting 1 minus P into 200 plus P into 8,000,000. This is nothing but the conversion between nanoseconds and milliseconds, right, and then finally we get this value. Okay. So, with this we can, by using this formula we can calculate the performance of a demand paging, and with this, that is all for this lecture. Thank you.